If you've been watching my previous videos, then you'll know that I'm currently investigating the noise issues on the Altair 8800 vintage computer and trying to find a way to reduce that noise. One of the things that's come up as a result of that is the need to find a robust, reliable and cheap memory card. You may have seen these in a previous video. These are boards I supply as bare boards and can be made up into the 16k version that you can see here. The problem with these is the chips are relatively rare. You can still get them, but when you're doing testing, especially intrusive testing of the type that I'm doing, you don't really want to be using these simply because it's too easy to damage them with the constant pulling out, pushing in, and also with the testing that I'm doing, it could damage one of the chips or the entire board. Also, if you use the Altair to any great degree, then you don't necessarily want to use your vintage boards. Keep them for special occasions, display, that sort of thing. So what I've decided to do to make it easier for me to do development work on the Altair is to create a drop-in replacement for the vintage memory boards. And what I've decided to do is to document that process through a series of videos so that anyone that's interested in the process can see how I go through that process from start to finish. And in this first video, then what I'll be doing is basically introducing the project and how I'll be going about the development process. So the first thing is we'll have a quick look at the schematic for that board. So this is the board I've just shown. It's quite straightforward. All we have is a series of buffers. This is the section that essentially decodes the board. So this is a 16k board, and it can be mapped to any one of 4 locations within the address space of the Altair, and that's done through the upper 2 bits. They're decoded. So you set one of these switches, and when the correct combination on those 2 bits is hit, then it triggers the logic within this board. The next 2 bits down are used to select the block within the memory array. So it's arranged as 4 4K blocks on this particular board. You then have an output latch, output tri-state buffers, etc. So this is relatively straightforward, and it's kind of the way most of these boards work. But one of the things that's very odd about the Altair, unlike most small computers which have some form of monitor program that resides in ROM, the Altair doesn't have that. You can fit ROM cards to it, but the basic Altair doesn't have any monitor program or ROM at all. So the functionality that you get for the front panel controls, for depositing data into the memory, reading it, that sort of thing, is provided entirely by the front panel. The issues that tends to generate is because everything is done in hardwired logic, then there are some oddities in the way that the machine behaves, partly because of the way that the circuit's designed, but also because of the physical arrangement where you have the discrete logic feeding into cards like this through a long series of wires and buses, and that introduces further problems. So overall the machine's a bit of a handful when you're trying to get various things to work on it. And that's one thing that I've found as I've been investigating it, is its behaviour can be a bit erratic sometimes, and that's what's prompted me into developing this memory card. So some of the main issues are that, unlike a computer that has a monitor program where essentially the processor, system, memory, etc. is always running, and all you're really doing is changing the contents of the program area, the Altair doesn't behave like that. When it's running, it's fine. It tends to behave itself fairly well, but the interaction between cards such as memory cards and the front control card can be a bit of a haphazard arrangement, because it operates in a very different way when you're inserting data, reading data manually through the front panel than it does when the machine's actually running. And there are some strange workarounds that have been incorporated to try to make it work reliably. So when I looked at the possibility of developing my own memory card for this, what I wanted to do was to come up with something that was relatively low cost and easy to build, because I will be making these boards available to anyone that wants them at the lowest price possible. I won't be providing them ready-made, but the bare boards will be available and the component count will be very low. So the idea is that anyone that wants a low-cost memory card will be able to build one very easily. So the first thing I tend to do when I come up against a new design, and I've started this just today, so you'll be going through the entire process with me, good bits and bad bits, so hopefully it won't be too traumatic going through all this. So first thing is, what I tend to do is come up with a very basic white paper design. So this is what we're starting with. As I say, it's intended to eliminate all the RAM card issues, and for everyday use or test purposes it provides an inexpensive alternative to using expensive original cards. So I wanted a 64k maximum capacity. I want it to be able to emulate between 1 and 4 16k cards, not necessarily in consecutive address spaces. In other words, to be able to select any one of the 4 blocks independent of the others. I want the entire cost, including the board, to be less than £60. I want it to be able to build it either as a 32 or 64k version. So if you don't need the full 64k, you can just omit some of the parts to reduce the cost even further. I wanted the design to be robust and stable. So in other words, I wanted something that could be used to fault find on the Altair without introducing a whole load of new issues that have to be worked around. So once I've decided on that, then I break down the steps that I'll be taking to go through this development, and I'll be releasing at least one video for each of these individual steps. So step 1 is to design the board control logic, then the memory interface for the memory chips themselves, output buffering, the memory block select decoding. Then once I've designed all this on paper, the sketches, whatever, then I'll start doing the schematic capture in the PCB CAD system. I'll translate that into a PCB, get some PCBs made, assemble the prototypes, do the initial testing, and then project completion is correcting any issues with the design, correcting any errors on the board, and then going through this last few steps again to make sure that it's stable and works the way it should. So as I say, I'll be doing a video for each of these steps. At the end of the project, I should end up with a design for a card that can be used as a drop-in replacement, but at very low cost. So the step 1 is board control logic. As I said, the Altair is a bit strange in the way that the board control logic has to be implemented, simply because of the way it has to operate differently from the front panel controls to how it operates when it's actually running a program. So to that end, I was looking at this design, and although it's not suitable in its present form, in a generic term it's a good starting point for a design for a card. And what I will be doing as I go through the project is showing how I'm translating this particular design into the new design, and how each individual section will be modified to suit the requirements for the new card. So my first decision was, what am I going to use for the actual RAM? So on this board, it's fairly simple here because it's not showing the RAM section, but this block here, the dotted area, is actually a block of 32 memory chips, the SEMI 4200 chips. But even though it's a block of 32 chips, it can be looked at as a single memory device. So what I opted to do initially was to replace this with a 64k SRAM. But then I'd decided that I wanted to be able to lower the cost further for anyone that only needs a 32k. So I changed that idea and decided to go for two 32k SRAM chips. So these are the ones that I'll be using. They're Toshiba TC55257s. They come in two general speeds and either one will work. They're both much faster than the ones that were in the original card, so they'll be fine. And that chip will effectively replace the block of SRAMs that are on the original card. So once we have this selected as the device we'll be using, then the next step is to determine what control signal this needs relative to the original design. Some other changes I'm making is that if you actually look at this, you'll see there's some oddities going on, and this comes down to the way that the 4200 SRAMs work. So firstly, you've got the address coming in that's inverted. That doesn't actually matter, it just means that the address that you're saving the data to is not the address that's on the address bus. But because it's consistently inverting it, it doesn't matter. It just means if you set all zeros, you get all ones, but because it will do that every time, it just means that you're storing in different locations than what's on the address bus. But you're selecting that same address when you try to read it back out, so it doesn't actually matter. What is different though is on the data lines, again, they're being inverted through these buffers. That means that what's being stored in the RAM is the mirror image, so to speak, or the complement of what's being sent or set on the data bus when it's being sent to the RAM chips. And again, that doesn't really matter. What might seem odd on first glance is that it's not inverted when it comes out, but that's simply because the 4200 RAMs actually invert the data when they put it out. So in other words, if it's inverted when it goes in and the memory chips invert it when it comes out, what you end up with on the output bus when you try to read data is the same as you fed into it originally. The fact that it stores the complement of that is not really relevant. So because I don't actually need to do that, what I will be doing is replacing these with 74245 for chips. So they are quite nice chips to use, they're quite easy to get hold of, they don't invert the data coming through, so I can also use them for the data bus as well. So in other words, all these lines will be replaced with 74 LS245s. I'll come back to that later when we start drawing out the circuits. The next section to look at was the decoder section. I'll come back to that on the next video and show how I'll be working out the decoding for it. It will be different from this because obviously we're not using 4 separate blocks, we're using a single block, so I can simplify this quite a bit. But I will need to change this arrangement because we're not doing 1 of 4, we're doing any of 4. So it'll be either 1 of 4 or 2 of 4 and not in any particular order, so this arrangement wouldn't work. But it's just a simple change in the logic to implement that. So today what I want to look at in more detail is this section. So I've done a blow up of that particular part. So what we have are the control lines coming in from the backplane. They go through a series of inverters and logic gates to generate the required control signals for the memory chip. There is a latch that's used to generate the required pulse, so there is no need for certain lines to be cleared because of the way the Altair works. Certain lines don't provide the required pulse that the memory chip needs, so that has to be done on board the memory card itself. So what I was thinking of doing was keeping a similar arrangement to this, but modifying the logic states so that it suits my particular memory chip, and also the output latch and output buffers may need different logic levels, but we'll come back to that another time. It's just merely a case of making sure we have the right levels going out. One important thing to consider, if you watch the video I posted on the JM processor kit, that's a discrete transistor microprocessor, and one of the points I made was that timing throughout the entire system can be important. So in other words, if you start adding or removing gates, then you need to make sure that the resultant timing of all the signals is suitable for your application. You can't just start putting in extra gates and making the assumption that the timing will still work out, because each gate is going to introduce a short delay, or even if you remove a gate, that can upset the timing as well. So that's something that we'll need to consider when we're doing the design. I thought what I'd do for step one is to have a look at the signals that exist on the current card, on the existing card. So in the manual for this particular card, it does give you timing diagrams for each of these test points, along with the input signals. So what I'm going to do is to attach the logic analyzer to these lines, and we'll have a look to see if the Altair is actually doing this, and if the timing on the machine itself matches the intention of the designers. Once we've done that, we can make sure that we fully understand what each of these lines is doing through each of the different phases of operation. So whether we're manually depositing or reading data from the memory card, or if we are actually running a program that is itself reading or writing to the RAM. So I'll get the Altair in, I'll get the analyzer hooked up, and then get back on camera and we'll see what the card is actually doing. Okay, so I've got the Altair hooked up to the logic analyzer. Hopefully you can hear me over the noise of the fan. And what I've got hooked up so far is test point 1. So this is the line that responds to the current value on address lines 14 and 15 to select the particular card. And what it essentially does is enable the logic to trigger the functions within this card if this particular card is being addressed. I've got test point 2, which is the pulse generated by the flip-flop that's used to time the memory access. And then we have the other test points, which are the read-write and the output enable. And these are of course used to control whether we're reading or writing from or to the memory, and whether the output buffer should be enabled. I've also included a fifth test point, which is the chip select enable line, and this is just the line that goes low whenever one of the blocks of RAM is being addressed. I've also got the 5 input control lines hooked up, and that means we can look at what the state of those particular controls are at any part of the memory access operation, and that might be useful so that we fully understand how to interface our card to the functions within the Altair. And as I said, that's the main thing when designing a board for the Altair. Is a bit of an oddball arrangement that needs to be taken into account. You can't just hook it up as you would a normal memory card. Okay, so I'll get the camera moved so that you can see the analyzer screen. Okay, so we're now looking at the analyzer. Hopefully you can still hear me. The Altair fans joined in to make even more noise. So the way I've got the analyzer configured is I've set up an input for each of the 5 control lines. So that's one for each of the lines coming from the Altair control bus. And I've also got one line for each of the test points identified on the schematic. I've also included a 5th test point to enable us to look at the chip select line that goes to the memory array. So if we go to waveform, I've got this set up to trigger on the test point 2 line, and test point 2 is the read enable. So this latch is used to generate a read enable pulse, and that in turn will allow us to access the data within the chip. And once the data has been output from the chip, it's then latched into the output latch, and then it can be optionally output onto the data bus. I'll do an examine and we'll see what data we capture. So we can see we're getting some data. I'll zoom in a little bit. But one thing you'll probably notice if you look at this and then compare these signals to the waveforms shown in the manual is that in the manual you're seeing skew between the various signals, and that's to be expected simply because the signals we're looking at are all on different parts of the schematic, and they have different numbers of gates between them and the source signal. So we would expect to see skew between the various signals. Now, anyone that's familiar with using these analyzers will know what's causing this and can skip through this bit. Anyone that's not familiar with these analyzers, I'll just quickly explain what we're looking at. The analyzer is currently set to state mode, and in state mode we feed it a clock signal. So in this case it's being fed with the main clock signal from the Altair. And in this mode the analyzer only captures data on clock edges. So in other words, it only captures data at discrete intervals based on the clock it's being fed with. And that means that any time we get a changing signal, the analyzer only sees that change at the next clock edge. So it appears that everything's nicely lined up, and in reality that might not be the case. So doing investigations like this, it's better to use a timing mode. So I'll switch to timing mode and then just explain what the difference is. So we're now in timing mode. I'll go back to the waveform display, and you'll see that we've changed from the number of states that we're looking at to actual times. So it's now acting far more like an oscilloscope, where it's taking readings at discrete intervals, and we can control the interval at which readings are taken. Currently I have that set to 8 nanoseconds, but we can change that if we want, and we can go down to 4 nanoseconds in this machine, or less frequently if we're not interested in as much detail. This machine's got quite a good memory depth, so we can go to quite short intervals. So I'll set it to 8 nanoseconds. It's quite enough for what we're looking at, and it will capture the propagation delay for a gate within this system, which is actually what we're looking for. So as I say, we're now looking at a system where it's taking measurements of the input signals at discrete intervals. So in other words, every 8 nanoseconds it will take a recording of the current state of all the lines, and that's what we will look at on the waveform display. So I'll set the trigger again, activate the same control on the Altair to examine the current memory address, and what we can now see is that there is skew indicated on the lines, which is what we would expect to see in a normal system. So as I said, we're triggering on the test point 2 line, and this is quite a long way into the system, so certain signals we want to look at will occur prior to that. We need to go back a bit through the analyzer memory to look at the various signals. If we now look at the expected data shown in the manual, we'll see that the first event we would expect in a read cycle is for the sync line, this is the P-sync line, to go high. And indeed we can see the P-sync line has gone high. And then if we follow through the timing diagram, we'll see that at the next rising clock edge we should see test point 2, the read enable line, going high. So test point 2, this red line is the trigger point, test point 2 is the fourth one up, and we can indeed see that at the next rising clock edge the test point 2 value does indeed go high. And you can also see on the diagram that there is, well, it's kind of vague, it's showing that there is a small amount of skew, which is not surprising because we do have at least one gate between that point and the original incoming clock line. Okay, so we can then look at the rest of the signals to see if they all match what we would expect. So if I go back to the schematic, we'll see that we have test point 2. Test point 5 is the bottom one, is the inverse of test point 2, as you'd expect, as long as this gate is enabled. It's memory right, so that this line means that this is currently in its enabled state. So the output here will go low whenever this is high. So in other words, this is the essentially the chip select line for a read, and test point 5 is the low value for the chip select that goes to the memory to select the memory. So this is important to keep track of all this when we come to designing our own board. Whether we decide to use this in its current form or modify it, we need to see what signals are being generated and in what relative timing slots they are occurring. We can then look at the rest of the signals. So if we look at test point 3 is the output enable. The reason that the Altair is a bit odd is that in order for us to be able to see the data value on the front panel, then the output buffer on the card, so if I get the diagram and just quickly show you this. So this is this buffer here. This also has to be enabled in order for us to see the data which is being fed currently through to the LEDs on the display panel. That's why we can see the data values that we load into memory or deposit in memory on the LEDs. You also notice, if you look carefully, there's a flicker of the LEDs between you doing the deposit and the value appearing, and that's because the data's being fed into the chip. It's then being latched into this register, and then this buffer's been enabled to put the value onto the data bus, and that's what we're currently looking at on the LEDs on the front of the Altair. So we need to make sure all these things still happen, and things such as the buffer we'll come back to on another video, and the same with the output tri-state buffer as well. But what we're looking at here is to see what the various signal levels are on these lines. So test point 5 will give us the chip select, and that's also used to store the data into the output register through another gate. It needs to be latched into this register on this board simply because the designers didn't want to have the 4200 RAMs enabled continuously, because they do draw a lot of current when they're outputting data, and they also get extremely hot, so it would have been a very short-lived board if these RAMs were just being enabled constantly. So rather than doing that, what they did is they had a short duration pulse, which is what this does, and then they briefly output the data. It's latched through the control logic into this register, and it's then available when it's needed to be output onto the data bus. And that's something that we'll duplicate. Strictly speaking, with the RAM chip we're using, we don't need to do that, but just to make it consistent in terms of timing with the way that the Altair operates, I'll do something similar, although I will simplify this arrangement. So going back to our waveforms, we can see that we have the read enable pulse going out. As I said, that's test point 2. Test point 1 is constantly low, so that is this line. So this is the card select line. It's constantly low, although it's shown as going low on the timing diagram. It's low all the time on this particular machine because there's only one card installed on this machine, and this line is normally just left by the Altair in whatever its previous state was, unless it's changed by a different address being put onto the upper 2 bits of the address bus. The other lines we can look at, the PD bin and test point 3 bus enable lines. So test point 3 is also the third one up, and we can see that that is going low at the point where it's supposed to. So it's bus enable, that's what's putting data out onto the address bus. So at the end of this cycle, you can see that while it's going low during the read, it's going high again at the end, and that's what causes the data to be currently output onto the data bus. So it doesn't look quite like this, simply because, as I say, these lines aren't always in the state that you would necessarily expect them to be in. But other than that, it seems to be working fine. I'll go through and examine this in a bit more detail. But now that we can kind of confirm that we are seeing the data that we're expecting, I can go through, look at the schematic and determine if I want to use this in its current form, modify it, and then in conjunction with the requirements of my memory chip and my output buffers, whether I want to change any of this logic or just use it pretty much as it is. So in the next video I'll put together this on a breadboard, we'll hook it up to the Altair, and then we'll make sure that we are getting the signals that we need, and I'll also make sure that those signals are tailored to meet the particular requirements of my memory chip and the buffer I'll be using. Okay, so that's it for this video. Any comments would be welcome. Hopefully you'll find it interesting as we go through the development to see firstly how I go about developing boards, but also how the vagaries of the Altair kind of drive this development.